All right, welcome to physics lesson 5.06. Now we have friction on an incline. So in case you haven't figured it out yet, we're kind of boiling the frog, where we're adding a new layer each time, a little bit like when you juggle. We start off with two balls, and then you add a third and a fourth, so on and so forth. Technically, you have everything that you need to be able to solve this problem. So I recommend you take a crack at it, see how you do, and then compare your answer to the end. If you're not quite feeling that bold, that's okay. We can walk you through it. So we have a 91 kilogram refrigerator on a ramp. The refrigerator begins to slide when the ramp is raised to an angle of 34 degrees. What is the coefficient of static friction? So the implication is the ramp is level and we're picking it up. Maybe it's like the back of a lift truck or something. And when it's at 20 degrees, it doesn't slide. 25, it doesn't slide. But when it hits to 34, that's the instant. So, and we pulled all of that out of the problem because it says begins to slide. That has some implications for us. Also, that coupled with the fact that we're looking for static friction. So remember, when we begin to slide, we know that static friction is this. Well, if we're at the moment where we're just beginning to slide, now we're talking about the part where it's equal. So they're equal. We also know, I'm going to refocus here. I feel like this is a little blurry. We also know that if we're at that point where it's just beginning to slide, that we have F net X is equal to 0 and F net Y is equal to 0. And that's going to come in to play in our problem solving strategy. So I'm going to give myself a horizontal and try to draw a 34-degree angle. So let's see, 45 would be here. So I think 34 would be about right there. I always feel like my angles are a little steep, but I do try. Let's throw a refrigerator on the ramp, and we've got 34 degrees. Okay, before we go too deep of a dive on this free body diagram, see if you can figure out what forces we're going to need to put. Pause the video if you need more time. So our forces here are our weight vector, our normal force, and the force of friction. If you said, and we're talking about static friction, you said, well, I have to have an applied force. No, nobody's pushing on the refrigerator. You're thinking, well, maybe I have to have an applied force to counter. You have to have a part of a force to counter. And what do I mean by that? Well, let's see what we can do here. As usual, let's start with the weight vector. And our weight here is 91 kilograms. If I multiply that by 9.81, and most importantly, and I probably should have put that on at the beginning, we're going to tilt our coordinate system. So positive is going to be down the ramp, and positive is going to be up. So that means for this, I'm going to have a negative 892 Newton force down. Well, my axes, according to my coordinate system, I'm going to do them in yellow because I can overwrite that pretty easy. So I'm going to have my horizontal axis is going to be down my slope. My vertical is going to drop down this way. So those are my axes according to my coordinate system. Before I draw my normal force and my friction force, I'm going to go ahead and I'm going to resolve this into F weight Y portion and F weight X portion. So I'm going to have friction going in the opposite direction, but do you see that the entire 892 newtons is not contributing to my motion? So I haven't done my motion analysis yet. If this begins to slide, this means we have no motion, but if I did, the motion would be here. So this is the component that's going to cause, if this once this refrigerator gets going, this is what's going to cause the acceleration right here. And the only reason it doesn't come down barreling like a bat out of you know where is because I've got some friction that's going back this way. So again, because we're at this begins to slide, I know that my friction force needs to be, I have an F net X here, it has to be equal to 0. So my friction force, if this comes down that far, this has to go back that far. So now my X, my horizontal vectors are equal and opposite. Same thing for the normal force. If I'm coming down this far, then my normal force has to come up this far. Now, once this starts to slide, what you're going to see is that this friction vector is going to drop because we're going to go into kinetic friction. And remember, the kinetic friction is less. So here's what happened. I started off and I was perfectly flat. I didn't have a friction vector. What's going to happen as I lift is that friction vector. So when I start off, let me kind of re-sketch over here off to the side. So when oh shoot, that was too far off to the side. Okay, let's go to this side. So here's my start. My refrigerator's flat. As we start to lift this at a small angle, a little bit of this weight vector is directed down the ramp, and I get a little teeny tiny, so let's say we're halfway between. Let's go halfway to this angle. You don't have to draw this, I just want to illustrate this point. So this is let's say this is at 17 degrees. My weight vector's got to be the same length. Weight doesn't change. But notice FWX is smaller. And that means that my friction vector is also going to be smaller. So that means that my coefficient of static friction is going to be in this category. It's going to be less than, so I start off here, I've got a 0, basically a 0, I have 0 friction, so I have a 0 coefficient of static friction. As I raise this ramp, this number gets bigger and bigger and bigger until I get to this point where I get to my max. Okay? All right, well, let's go ahead and work out this and this. So this is 34, because this is 34 degrees. This is going to be 34 degrees. And this is an adjacent. Remember, cosine is adjacent over hypotenuse, and this hypotenuse is negative 892. So I'm going to have negative 892 cosine 34, and I'm going to have negative 892. It's going to be opposite sine 34. Whoops, positive. Down the slope is positive. I had a wrong sign there for a second. So that means this guy is going to be 500 newtons. And this guy's going to be, if I can read my writing, cannot read my writing, that's pretty bad. So let me punch cosine 34 into my calculator. I'm going to have 739.5. Well, to solve for the coefficient of static friction, I need my normal force and I need my friction force. But here's the nice thing about this problem. Remember, these vectors are equal and opposite. So if this is positive 500, this has to be negative 500. If this is negative 739.5, this has to be positive 739.5. To solve for this, all I have to do is plug those values in. Negative 500 equals mu sub s 739.5, and that gives me a mu sub s of 0.67. So I started off at 0, and as I raise, I'm going to watch that coefficient of static friction go up. So here we might be at like 0.3. If I go up another 5 degrees, I'll be at 0.4, and then this is a max. So once I hit this, I'll be there for a split second, then my movement starts and I shift over to kinetic friction. Different ball game, same formula. Okay, if you're jumping to the end of the video, is this what you got? Did you get it right? We did end up doing some discussion on the difference between uh, static or coefficient of static friction when it goes from, so here we said the coefficient of static friction is 0. Halfway up, it's going to be at about 0.3. This is my max where it's going to be at about where it's going to be 0.67. All right, so you've got quite a few practice problems with this. Actually, 2 of the sections are frictions on an incline. Remember, our numbers don't necessarily match up, so take a crack at those and be sure to email me your questions. Thanks and have a good day.